Today we're going to see why you can spot a face in an electrical outlet, why experts see things that novices don't, and why one small patch of brain tissue started an argument that still hasn't been resolved. So this is our continuing look at perception and our continuing delving into that mysterious thing that we are trying to understand, known as the human mind. And we are again going to focus in on a very specific ability of the human mind, and that is perception. That is the ability to have internal experiences, internal sensations brought about by external stimuli. And as we're going to see, that those sensations serve a purpose, such as being able to navigate through an environment, being able to identify different individuals, being able to basically interact with the world that we are situated in. And last time we started our look at perception by talking about times when perception is accurate, such as when there is a rabbit in the field and you see a rabbit in the field. And then sometimes when your perception is inaccurate, specifically with illusions. And we introduced the idea of top-down versus bottom-up processing. And for a long time, perception researchers argued about which one was correct. Is perception mostly top-down? Is perception mostly bottom-up? But the real question isn't which one is right. The real question is, what forces your perceptual system to use one versus the other? So that's what I wanted to pick up with today. So as we saw last time, we took a look at three kind of illustrative stimuli. One was Bev Doolittle's painting of Pintos. The other one was the bent pencil illusion. And then the last one was Al Held's picture, the big N. And the challenge that I left with you was to try to determine why the broken pencil seems to be mostly bottom-up processing, why the painting the big N seems to rely mostly on top-down processing, and why Pintos is a mixture of the two. So what are some of the ideas, some of the speculations? What is going on in these scenarios? Mm-hmm.
On the first one, there's kind of like two parts to it that you can kind of get. The bottom half of the cup and then above, the bottom half of the water and above the water that you kind of can put together, which would lead me to mind why it's bottom process. I mean, bottom processing, since you have to take those parts and build up the idea of it. Or with the course image, you have like the form that you have to break it apart and take it to the environment out in order to make the full image of what's going on.
Okay, so you're saying that on the left with the broken pencil illusion, you kind of have two very distinct, I guess, situations. You have in water and out of water. And then that requires you to do bottom-up processing. Can you explain again why? I just want to make sure.
Well, I mean, I'm not kind of the greatest understanding bottom up, but just because you have to form the understanding of the cup, the pencil in the water, and then form the understanding of the pencil out of the water, and then combine those understandings to get the full understanding of the pencil resting in the water, both in and out of it. I'm not sure.
Okay. Yeah. Yeah, I'm trying to summarize it. So it would actually kind of seem that that to be more of an argument that it's top-down processing in that sense, because that elaboration that you made kind of suggested that you know things about a pencil, you know things about the water, you know things about the glass, and then you try to combine those together. And the more you bring into the idea of knowing certain characteristics of things, that's more top-down of an argument. And it would be a testable theory to actually contradict what we sort of brought up in class and say that that one on the left there is actually top down. So we labeled it as bottom up. But given your explanation, you could actually make a theory that no, that's actually top down. It's just that you're missing one piece of information, which is the refraction of the light rays. So you know things about a pencil, you know things about water, you know things about a cup, you put all three of those together, and the only way that all of those things can make sense, given the information that is coming in, is for you to say, well, that pencil has to look like it's broken. So that would actually lead to a kind of testable theory where you would want to set up situations that required that kind of combination, but with things that we did not know anything about. So with like some sort of novel objects that we didn't know how they operated, we didn't know exactly what they were, but they were combined in a way. And if they still led to an illusion and we didn't know anything about them, then that would argue that no, this is bottom up. But if it did not lead to an illusion and we didn't know things about them, then it would argue that this is top down, because we're getting an illusion because of the knowledge. We are, rather than I kind of lost my train of thought there as well. Rather than if we didn't have that knowledge, we would get the actual true image of it, of a straight pencil. So very cool idea, very testable theory, but it would put that glass into the top-down category according to that theory. So does anybody have any other ideas about that would keep the glass in the bottom-up category? Yep. Okay, well, no, let's bring it up. Who knows where it'll take us?
For the big N, I thought the reason that I was able to identify it is because it felt, I could recognize it as like a big bubble letter almost.
Mm-hmm.
It's like if I was going to carve out a shape into that letter, I just take the little bits out. And how graffiti is more about presenting an image and a feeling along with the letters, like the shape of them is important. I took a second and stepped back to look at it, and then I saw it.
Okay. Do you have experience with that type of art?
There was a whole unit in my senior year high school art class about graffiti and doing graffiti work, and it was really interesting. So it kind of stuck. We also did art and doodling on your paper that I had since fifth grade, so I thought so it's more familiar to me to look at the bigger picture.
Okay. All right. So let's roll with that. That's actually a really good way to kind of take this a step further. So you were saying that when you took a look at the big N, the one on the right there, you just thought to yourself, well, if it was a bubble letter, if it was like graffiti lettering, well, then that would be an N. And part of the reason that you might have been able to do that was because you took a unit in your art class in high school that had to do with graffiti art. All right, so we have, in our class, we have one person that was able to identify the big N without any help from any other knowledge that I gave them. I don't think anybody else identified the big N before we mentioned what it was. Did anybody else take a art class prior to this class where graffiti was covered or bubble lettering was covered? So hands up if you did. Okay, so we have one individual that took that class and was able to identify the big N. We have a bunch of other individuals who did not take the class and were not able to identify the big N. So what might that say about the role of top-down processing in this case? Mm-hmm.
Being familiar with something and being able to see it a bit more abstractly because you understand the beauty can lead you to recognize things that would be easily missed by other people. Like, for example, a doctor might be able to cure something wrong with someone's heart that, someone else couldn't, or they would recognize their vein was too large or unable to be met, that anyone else would be like, I have no clue, I didn't cook them the first day.
Okay, so I want to concentrate on the first part that you mentioned, being familiar with something. Being familiar with something definitely allows you to perceive things that other people won't. So the clearest examples that you're going to have so far in this class of being able to be familiar with something and then completely not miss anything is the moonwalking bear You will never miss the moonwalking bear again in that video. The whodunit, you will notice way more many changes than you did the first time through the whodunit. That big N will always be the big N. If you actually go to the museum where that is hung up, you're going to walk in there and there's going to be people that are confused until they look at the plaque and read the title. But you're going to go in there and you're going to say, oh yeah, that's the big N. So familiarity in these contexts is really just another word for knowledge, right? If you're familiar with something, that means you have knowledge of it. If a doctor is familiar with the patterns of a heartbeat and the patterns of how blood sounds when it's rushing through the veins, they'll pick up on things that other people will miss because they have that top-down knowledge that they can bring to the situation. So it's really, really cool that we had one individual that was kind of familiar with potentially this art style and use that knowledge to say, oh yeah, no, that's a big N. But everybody else without that knowledge needed help before they could see it, needed to be provided with that top-down prior knowledge before you could see the big N. So if we were to summarize these three pictures, which one would you say required the most top-down knowledge before you could perceive it? Which one would you need the most information before you could perceive it? How many people think it's the pencil in the glass? Hands up. How many think it's Bev Doolittle would require the most top-down knowledge? We have a few more hands. How many think is the big N? All right, we have a bunch of hands. So the general consensus is that you need the most top-down, or you need the most extra provided knowledge for the big N. You need some extra provided knowledge for Bev Doolittle's Pintos, and you need the least extra provided knowledge for the pencil in the water. Now let me ask you this. Out of the three pictures here, which one, just as a stimulus alone, has the least amount of information in it? So how many think the big N has the least amount of information? All right, quite a few hands. How many think it's Bev Doolittle's that has the least amount of information? All right, we got no hands. How many people think it's the pencil in the water? No hands at all. So the big N seems to have the least amount of information. The big N seems to require the most top-down processing. So what that actually means, or what that actually really implies, is that if you have enough information in the stimulus itself, your system stays bottom up. And that pencil in the glass is a really nice example of that. Even when we provided you with extra information, even when we provided you with that physics lesson about how light refracts, the stimulus itself has enough information in it to cross this threshold and it stays bottom up. But when your information is not enough, then you need your mind, you need that prior knowledge to fill in the gaps. You need that knowledge to know exactly what you're looking for, because the knowledge in the stimulus itself did not reach that threshold. So in every single case, whether that knowledge came from a prior art course that you took, or whether that knowledge came from you being told the title of the painting, you needed that extra knowledge before you could get that stimulus up to threshold. And this is one of the reasons why illusions are so very useful. And perceptual errors are so very useful, because perception is a negotiation between what's coming in bottom up and what's coming in top down. And those illusions tell us where that negotiation breaks down and what those kind of terms of the negotiation actually are. All right, so any final comments before we move on from top down and bottom up processing? All right. So on our agenda today, we are going to continue our look at perception. We're going to take a look at a very special kind of perception. So we're going to start with experience-dependent plasticity, and that is going to lead us into a look at face perception, and specifically whether faces are special stimuli that we have a dedicated area in our brain to process? Or are they simply highly trained stimuli because they're incredibly important for our survival, and we just get highly, highly trained on our facial perception? So we're going to tackle that debate today, but before we get there, we're going to take a look at CogLab number 2, which was the spatial cueing CogLab, and take a look at some of the implications for spatial cueing in terms of how your attention can actually be manipulated and moved around. All right, so to jog your memory in case this was a little bit too long ago. So in CogLab 2 spatial cueing task, your task was to respond to the appearance of a red square as quickly as possible. So as soon as that red square appeared, you had to just indicate, boom, press the button, yes, it appeared. It could either appear to the left or the right of a fixation point. And during each trial, you were asked to keep your eyes focused on the center and to avoid moving your eyes. So in this case, you would get a fixation point and it would be across, and your instructions were to maintain your eye contact or eye fixation on that cross. Don't move it around, and then detect the target, the red square, as quickly as possible. In this situation, there were 3 conditions. There were the neutral condition, the valid condition, and the invalid condition. And in the neutral condition, there was no arrow presented in the trial. However, in the valid condition and in the invalid condition, you did have an arrow, either pointing to the left or pointing to the right. And in the valid condition, the stimulus actually appeared where the arrow pointed. So that red square would pop up in the same direction that the arrow pointed. In the invalid condition, the stimulus appeared where the arrow did not point. So in the valid condition, the arrow was telling you the truth. In the invalid condition, the arrow was lying to you. And then just to make sure that you did not ignore the arrow, just to make sure that you didn't learn through trials that the arrow was actually useless, 80% of the trials were valid. 80% of the trials with the arrow were valid. So the arrow was pointing in the correct direction. 20% of them were invalid. Arrow was pointing in the opposite direction. So the arrow was useful. It was just like an unreliable narrator. It told you mostly the truth, but sometimes it lied to you. So it would be to your benefit performing on this task to listen to the arrow, even though 20% of the time it actually did lie to you. So let's take a look at what that would look like. So in the neutral condition, you would start your trial. You would be fixated on that cross in the middle. The cross would change to the neutral stimulus, so it was not an arrow, and then the red square would appear, and you had to indicate as quickly as you could when that red square appeared, when you detected it. So this is a reaction time task, seeing how quickly you can respond perceptually to a stimulus. In the valid condition, looked like this. You would have your fixation point, and then the fixation point would indicate to one side of the display there. So in this case, it would be pointing to the right. Your instructions were still to maintain your eyes on the fixation point. So you were asked not to move your eye fixation or your eyesight to the side where the arrow was pointing. Stay maintained on that center, but a red square would appear on the right. And then in the invalid condition, this was the lie condition, you would be staring at the center at the cross. It would change into an arrow pointing to the left. You would still be staring at the center, but this time the square would appear on the right. All right, so what happened? So again, this is data that is compiled from both your performance as well as combined with performance of other people, other students doing CogLabs. So here on the x-axis, we have the 3 conditions: neutral, valid, or invalid. So neutral, no arrow; valid, arrow tells the truth; invalid, arrow is lying to you. And then on the left side there, we have reaction time in milliseconds. So on our scale here, it goes anywhere from 1/3 of a second all the way up to about 40% of a second. So it's 31% of a second all the way up to 38% of a second. All right, so what happened in these trials? So the neutral condition, this is kind of like your control condition. This is sort of your baseline for how quickly you can do this task. And that one clocked in at about 360 milliseconds. So red square comes up, and 360 milliseconds later, you're able to say, yes, I detected, I found that red square. In the invalid condition, it took you longer. So in this case, it was about 375 milliseconds in the invalid condition, where the arrow pointed you to the wrong side of the display. And then finally, we have the valid condition, and the valid condition was where you were fastest. So you were fastest in the valid condition, only about 335 milliseconds response time, and then you were slowest in the invalid condition. So fastest in the valid condition, slowest in the invalid condition. And before we go into the implications of this, I do want to pause here for a moment and hear some responses from you, because one of the things that you would notice if you were to take a look at the actual times for these different conditions is that we have that valid condition, and let's say that it's about 340 milliseconds, and we have that invalid condition, let's say it's about 375. That's only 35 milliseconds of a difference. That's 3% of a second, right? That's almost instantaneous. Only 35 milliseconds between the valid and invalid condition. So when you look at that, what is your kind of gut response? Do you think that difference is actually meaningful, or do you think it's basically noise? Mm-hmm.
I mean, it's kind of relatively not impactful because it's just a small difference, but maybe more relatively to like the neutral, the valid is still like pretty different compared to the invalid. It's still pretty good deviation between the two. So I feel like it's still pretty consequential. It matters.
Okay, so you think that it is meaningful?
Mm.
Okay, does anybody want to argue that it's not meaningful, that this is just noise in the system? Okay, well, I do agree with the general consensus and your idea there that it is a meaningful difference. One of the things that we are going to see, we're going to do signal detection really, really quickly. One of the, not really quickly, we're going to be doing it in a couple of weeks. One of the things that we will see is that your system has noise in it, and that is just the way systems work. So any system, any signal, either detection or signal broadcasting system has noise in the system. So always be aware of that. There always is some noise in the system, but this is a pretty reliable difference, and it is a meaningful difference. So what might this tell us about our mind? This 35 millisecond difference. Does anybody want to speculate about what is being bought with that 35 seconds? Yep.
I feel like your perception's kind of getting primed there. Like you're more on the lookout for something. And in those situations, you're looking out for it. In the valid condition, you're looking out for it where it's still speed is why it's quicker. But in the invalid condition, you're looking out for it where it's not going to appear. So, which is why you work slowly, because you're looking for it in an area where it's never going to appear. So it's going to take you extra time to fix yourself and be like, oh, it's over here now.
Oh, okay, yeah. So the idea is that this 35 milliseconds, that is the actual cost of you being pointed in the wrong direction. That is the actual amount of time that it took you to move something from that incorrect location to the correct location. So in that case, the neutral condition would be the time that it took you to go from looking at the center and putting resources at the center. I'll put it that way. It would be the time that it took for you if you put your resources at the center and then you had to go to one side. That's what the neutral time is. The valid time is you having your resources where they need to be. And then the square pops up there, and the 335 milliseconds, that's just how long it takes you to register and respond. The invalid time is your valid time. How long does it take you to register and respond? But the difference there is how long did it take you to take your resources from the wrong location and sweep that across the screen to that other location. So I kept saying resources because it's not your vision, it's not your eyesight that you moved, because you were supposed to stay fixated on the center fixation point. And I will admit, I have done this experiment and I sometimes forgot to keep myself fixated on the fixation point. So if you're sitting there going like, oh, well, there were trials where I didn't actually do that. Yeah, we're human. We're going to go where an arrow tells us to go. But most of the time, this is very consistent with highly trained participants that do this kind of work as well. So on the whole, we did what we were supposed to do. So I kept mentioning your resources here, your resources there. What is your resource that got moved in this scenario?
Attention.
Yes. So it was your attention, and specifically, it was your covert attention. So these milliseconds are actually measuring how long it takes your mind to move its covert attention from one side of the screen all the way to the other side. So valid condition, you're there where you're supposed to be. You don't have to move your covert attention. Invalid condition, you're on the opposite side of the screen and you gotta move your covert attention to the other side of the screen. All right, sweet. So that's the reason that we're faster in the valid condition and worse in the invalid condition, because we're moving our covert attention to the wrong location. We're moving resources to the wrong location, and then it takes a cost. It takes processing. It takes time to move it back to where it's supposed to be. So in that valid condition, the arrow tells you exactly where you need to be. No moving is required. In the invalid condition, arrow lies to you, puts you in the wrong position. You gotta expend resources. You gotta expend processing power to remove or to move again your attention, your covert attention to the other side. That costs approximately 35 milliseconds. All right, so in this case, we have kind of two effects occurring here. We have endogenous and exogenous attention in this particular CogLab. So does anybody want to take a guess or speculate about what is the endogenous, coming from inside, stimulus is grabbing you, attention aspect of this CogLab, and what is the exogenous, attention is coming from outside, goal is directing you portion of this CogLab? Okay, I'll give you a hint. In terms of being endogenous or exogenous, one of those is the arrow, and one of those is the red square. So let's start with the endogenous. Which one of those is more likely to actually grab your attention? The arrow or the red square? The red square, right? The red square. There's something about red on a black background. It's unique. It's salient is a favorite word of cognitive psychologists. There's something about it that you don't need to be told anything about this experiment. If you were just sitting down in front of this computer and mistakenly started this CogLab and did not read any of the instructions, as soon as that red square popped up, you'd be looking at that red square. On the other hand, the arrow, that's exogenous. And it's exogenous because that is goal directed. That is something where you need to know what an arrow means, and you need to be told, arrow's gonna tell you where to go. And when you see the arrow, there's nothing about it that grabs your attention and actually moves it in the direction of the arrow. It's something that just tells you where to go. It's something that gives you a goal and says, hey, why don't you move your attention over there? So whenever you see an arrow, it's not like you're you have to fight to be like, don't look where arrow's pointing. You just say, oh, there's an arrow. It's pointing over there. I'm going to look over there because I'm going to follow that particular goal. So this is a nice example of endogenous and exogenous attention. And that is why the arrow had to be valid at a higher percent than it was invalid. Because when it's valid, that means that it's serving your goal. That means that you'll still use it to achieve your goal. That means that it still has that exogenous attention. But if it was 50-50, or if it actually, well, let's keep it at 50-50. That's the clearest example. If it was 50-50, you would very quickly learn that the arrow is not helping you out to achieve your goal, and you would be able to ignore it. And ignoring something means that it has to be exogenous because it's no longer serving your goals. Endogenous just keeps grabbing you. You can't just decide to ignore it. You would actually have to learn and train to be able to ignore that. All right. So we're going to take a look at some applications of this. So once again, we want to make sure that when we take a look at CogLabs, we actually try to bring them into the real world, try to see how they can actually inform how we interact and how we approach issues and problems in our real world. So we're going to start with a more of a fun one. But basically, this idea of spatial cueing and this idea of taking your covert attention and moving it to a specific place is basically one of the hallmarks of any sort of magic trick. So for a nice example of this, we'll turn it over to Penn and Teller.
Ladies and gentlemen, Penn and Teller! Oh my goodness! Nice to see you, buddy. Pleasure to see you. Thank you again. Welcome back to the show. First of all, I want to congratulate you on, you guys are the longest running headlining act in Las Vegas.
In history.
In
Not
history.
just now, the longest running headliner in history in Las Vegas.
Congratulations, that's just amazing.
And we just signed for another 4 years, so till 2022.
At the Rio.
We intend to die in office. That's our plan.
Oh, man, I can't believe I love that. Now, let's talk about the 5th season, Penn and Teller Fool Us. Explain the show to people if they haven't seen the show. It's a good premise.
Greatest magician in the world, and as we're into the 5th season, it really is the world. Get people from all over. They come on and they do a magic trick that they think can fool us. Yep. And if they can fool us, they come out and play with us in Vegas at our theater, the conveniently named Penn and Teller Theater. And if they don't, they go away crying.
Yeah, exactly.
And this season, we're also bringing back, which is not thrilling us, we're bringing back people who fooled us before. Fan favorites to come back on and try to fool us again. Yeah,
okay, now you always bring a cool thing or do something amazing as some type of illusion or trick, and so you're doing something tonight. I never know what it is.
Yeah, we didn't let you in on the rehearsal. But
No, I never know. All right, good.
What
do I do?
Yeah,
Yes.
stay right over there.
Okay.
We're going to watch it right there.
Okay.
You know, there's a word, misdirection, that's used by lay people a lot. It's a magical term. It's a term of art. And the way lay people use it is wrong. Because lay people often use it as a synonym for distraction. Like, hey, look over there, do something sneaky here, and then you look back and the trick's done. That doesn't fool anyone. Mm-hmm. The way we use the word misdirection is kind of a curating of attention, giving the audience a story that can tell themselves that lets them not really know they were distracted. We're going to do a trick right now using misdirection. I'm going to tell you what it is. The trick is the vanishing chicken. There's a chicken in there, we're going to make it disappear. Now, when I say give you a story to tell yourself, it's not some jive-ass story like this is Clucky McCluckface and this is the chicken coop rocket ship to Mars. No, a real story, which is you know it's a vanishing chicken. I've told you that.
Yes.
You know we're Penn and Teller. You know we do magic tricks. So as soon as I cover up this chicken, you're telling yourself what you're going to do. You're telling yourself a story. You're making yourself a promise. Because you're promising yourself right now that at no time will you allow your attention...
Oh, my goodness.
Misdirection. Now, Jimmy, I want to see how well this works. Can we have the house lights up so I can see people? Yeah, just want to see. Show of hands. How many of you saw the gorilla with the cymbals? Should be everyone. It's a goddamn gorilla with symbols. Should be all of you.
Yes,
Good.
yes.
Now, subset of that, how many of you saw Teller walk out here, cop the chicken, and split? That's almost everyone, too. Now, here's where the misdirection comes in. How many of you, during all of that, saw Sneak the gorilla into the cage? How many people saw that? Because that's misdirection.
Oh, my
right
God.
there. That's Georgie Bernasek who works with us. Georgie
Gosh,
Bernasek.
are you kidding me? Oh, my gosh.
Well,
That is...
Only we would take a showgirl and put her in a gorilla outfit.
I think even my computer was freaking out when that reveal was done. It literally almost, I think, you know what? That's your Turing test right there. If you can blow the mind of a computer with a magical trick, then that is actual intelligence. Okay, so that was a nice example of misdirection. I also like the fact that apparently in any sort of change blindness studies, gorillas are just the go-to stimulus there. But all right, so they just did a trick there where they said that it wasn't just look over there, but it was a way of curating attention. So the audience has a story, so that the audience buys in. But what it really is it's much like what we had in the spatial cueing, which is where through this story, through this narrative that they set up, through your prior knowledge of how magic trick works, how these magicians, who they are, the fact that you're watching a magic show, the fact that when the gorilla walked out with the symbols, I don't think anybody honestly thought, oh, well, this must be the trick here, right? This is really what they're trying to do. You knew that it was something else, and yet still they were able to produce this trick to get you to pay attention to the wrong thing so you weren't be able to see what it was. So whether it's a story of a magic trick or whether it's the story of an arrow pointing you in the wrong direction, they were able to buy those 35 milliseconds or longer enough to make sure that the cost of processing what you needed to process was not there, and that those changes were things that were not detected. So when you're shifting your attention and you have limits of awareness, can anybody else think of situations in our world today, or maybe in your own world, where your attention is being misdirected in like different directions? Yep.
Any social media, any website ever with ads.
Okay, so any social media or any website ever with ads. So those are two different things. You want to elaborate one?
Really, any website or app that you go on, there's going to be built-in ads that make you look, make you think that it's part of, oh, it's just another post, but it's an ad. It's something, or you get a pop-up before every video.
Mm-hmm.
So whenever you're forced to look at it.
Okay, so one example of your attention being curated, of your attention being moved in such a way that it's maybe misdirecting you from your goal, right? You just wanted to watch some entertaining videos and you end up watching a whole bunch of ads. That's an example of this phenomenon of the spatial cueing, right? So in this case, when the ads are very kind of catchy, very or sort of in your face, I'll just use the term attention grabbing, right? You know, sometimes you're just scrolling through and then something just like pops and you're just like, oh my gosh, what is this? And you're like, oh, it's an ad, let me keep going. If it's attention grabbing like that, then that is an example of the exogenous attention, the actual stimulus of it grabbed you, pulled you in, and before you were able to realize what you were looking at, you were already being sold to, you were already being advertised to. And then on the flip side of that, when you mentioned, oh, but there's sometimes you think, oh, I'm watching a video, but I'm actually, then you realize, oh no, this is an ad. That's an example of an endogenous grabbing of your attention, a goal-directed grabbing of your attention, because you were thinking to yourself, well, I just want to watch, some fun videos. And then you're there saying, well, this is a fun video. This is going to help me attain my goal. But then it's like, oh no, this is an ad. So it's as if social media has this arrow, and the arrow is saying, hey, look over here. This is a fun video. And you look over there, but it's not a fun video, it's an ad. So it's the goal-directed attention that can also get you to have your attention be curated. Anybody else? Yep.
So a good example of distraction would be specifically kind of what we've seen with the TikTok generation, but it's used very predominantly in Asian advertising specifically, where it introduces a bright light, typically, I'm not sure why, but I know specifically a circle becoming larger, attracts the eye, might have something to do with movement, thinking that you're displacing yourself, loud noises, and typically something that is dysmorphic or acute in a way. It can delve into the uncanny valley, but it has to get some type of relatability right out the gate. This is why, like TikTok with the butterfly filters and
Mhm.
like that has kind of become the new marketing. I don't want to say go-to, but it's the terrible cartoons from the 2010s that Facebook tried to push it out. I'm sure you remember your office work and such.
So yeah, so a lot of different endogenous stimuli, things that grab your attention. So things like bright lights, those grab your attention. You don't have to be told to look at the direction that bright lights pop in. You see a bright light in the periphery of your vision, you're going to turn to that bright light. Things that sparkle oftentimes grab your attention. There's an evolutionary psychology theory that had to do with the fact that one of the only things that sparkles in the natural world is water, and water was extremely important in our survival. So if there was a lake and the sunlight was hitting it and it was sparkling, your attention would just go there because that was an important resource. So we have bright sounds, loud sounds. Motion is also a very important grabber of your attention. So if you want to just check this out on your own, go back to the whodunit video. And when I play that whodunit video, I tell everybody, make sure that you're looking for the inspector's coat. Does the inspector's coat change? Everybody gets that. The next change that is the most often noticed change is when I believe it's a bear changes to a knight of a suit of armor. And the reason for that, I believe, is because when they pan across the suspects, when they tell the inspector where they were, the suit of armor is still kind of rocking back and forth because it was just moved there. And it's very subtle, but it's enough. It's enough motion. And that motion is something that grabs your attention as well. That's why when you're looking for somebody in a crowd and that person sees you and they're trying to get your attention, what do? They'll yell your name out, and they'll wave, right? They'll be like, hey, over here, because that motion grabs your attention and all of a sudden you're looking at that person. The Zoom thing was really, really interesting because that is one of the only things that will grab a baby's attention. If you want to get a baby to react to a stimulus, and I mean like a newborn baby, there's really two big things that they react to. One of them is going to tie into the upcoming portion of this lecture, which is faces. Babies will stare at faces. There's a reason why parents, when they look at their babies, they bring them right up to their face, right? And let that baby see that face. Babies will concentrate on faces. Babies will react to a stimulus when it is looming. So the term is looming. And what looming is when a stimulus all of a sudden expands very quickly. And you are programmed, it is hardwired in your brain to respond to a stimulus that expands very quickly because that is something that's about to hit you in the face, right? That is something that is just coming straight at you. That's the only thing that looms, is expands very quickly because it's about to hit you in the face. So that grabs your attention. So filling these ads with those kinds of stimuli just means that they're going to grab your endogenous attention. and you're more likely to spend some time on that ad. And then when you direct your attention to it, it costs resources, it costs you time, and it costs you processing power to get back out of it. So those are some really, really nice examples. Another example, and the reason I like this Penn and Teller example here is that we saw that your attention can be grabbed and it can be misdirected, and there's a cost to it in a very small millisecond, you're looking for a square type of situation. But then we also saw that your attention can get hijacked in a much longer, much more complicated magical trick situation. And that is something else that is happening a lot of times when you take a look at the news cycle these days. So one of the things that the news loves to do these days is report on things that are not actually news, things that are not actually important, things that are not actually going to make a difference, but things that are attention grabbing. So one political analyst that I was watching a short video on YouTube one time, and they said that one of the biggest issues that faces the most people in a well-developed country is potholes. So if you are driving today out on some of these streets, it's like obstacle course there for your car. You're weaving in and out. And potholes affect millions of people. But when was the last time you saw a politician run on potholes? It just doesn't happen, right? Even though that would be one of the big things that affected everybody. But there are other hot button issues, other fire wars that get started, not fire wars, flame wars that get started. And that is basically your attention getting curated away from what is actually important to process. So it's the idea that you have an important issue, and that's the issue you want to detect. That's the issue that you want to spend your processing power on, because that's the one that'll actually make this world better. But then what you are told, actually, this would be the good one. If you're told, hey, you know what? It's important over here. Make sure that you pay attention over here. Look over here. Well, your attention is already there. And then you can not spend time finding that important issue, but actually spend your resources understanding that important issue. But what oftentimes happens is that we have a news cycle that says, hey, look over here. Look at this outrageous thing, or this thing that is causing people to get angry, or my favorite, the latest TikTok challenge that teenagers are doing. Isn't this a stupid thing to do? And meanwhile, you have all these other issues that are actually affecting people, actually affecting individuals, but you just don't have the processing power anymore because you've been distracted so often in so many different places that by the time you pull your attention back and pull it away, you only have so much attention to give. So that important issue stays under processed, under looked at, and it's this idea of your attention being cued and being sent in the wrong direction. All right, so any final comments on that before we leave our look at spatial cueing? All right, so attention, as we see, decides where your mind is going to spend its resources. Now we're going to take a look at what happens when there's a category that is so important that your brain actually might dedicate hardware to it. So this is one of the few times we're going to talk about the brain, because this is very informative in terms of how we represent the stimuli, and that stimuli is faces. So there's a debate that is going on where basically everything that we said about attention becomes explosive when your stimulus is a face. So faces don't just get processed. They get processed fast and automatically. And faces get processed sometimes even when there's not a face. So the question that we're going to ask here today is whether or not our minds, and by extension, the brain, has machinery that is special for faces, has dedicated processors set aside for faces, or is the pattern of perception that we're going to see for faces just what happens when you train something over and over and over and over again. So faces are one of the stimuli that we see the most, whether it's other people's faces, whether it's your own face in the mirror when you're getting ready to go outside. And like I just said, one of the first things that a newborn baby sees when it comes out into our world is faces. They give it to the parents, and what's the first thing that a parent shows their newborn child? It's not their shoulder, it's not their leg. They bring it right up to their face and they say, hey, check this stimulus out. You're going to be looking at these for a while. I will say it's always weird when you break things down that are very meaningful and magical in the real world, and then you're just like, oh yeah, parenting is putting that stimulus in front of that newborn. It'll wait until we talk about romantic interest. But anyways, I digress. All right. So why are we even discussing whether we have why are we discussing whether or not the special processor that we seem to have for faces is because it was built in or because we're highly trained on faces? Well, the reason is because we do have this ability in our actual brain, and then this gets implemented into the mind of experience-dependent plasticity. And what that is, it's a mechanism by which the structure of your brain, how your brain is wired, the actual physical wiring, is changed by experience. So what they did, one of the first studies that showed this, they took a look at chess players and they thought to themselves, is there a difference between how chess players process a chessboard when they're experts versus somebody who's a novice, right? Might that explain why expert chess people are so much better at chess? And Bilalic and Campitelli in 2018, they actually took a look at the activation and structural changes in a brain associated with expertise by taking a look at expert chess players. And what they found was that when you take a novice and you take a look at their brain activation when they're looking at a chessboard, we have the left side of the brain on the left side of the screen. That's awesome. We have the right side of the brain on the right side of the screen. Pay attention to the areas with the circles. The lighter the area, the more activation. So gray is not activated, white is very activated. And in those circles, you can see for the novice, they are mostly gray. Mostly gray, not a lot of activation. However, when you show chessboards and chess positions to an expert chess player, their brain doesn't look like that. Their brain looks like this. So those previously dark areas that are not active, when a novice looks at these chess boards and chess stimuli, those areas light up. They get recruited. They're used by the expert now to process information related to chess. So this is actual evidence of experience-dependent plasticity. These neurons over here were not chess neurons before years of practice, but after years of practice, those neurons there became specialized chess neurons that activated when they saw chessboards. So the reason that this idea of experience-based plasticity is important is because there is this region of the brain. So here's another image of the side image of a brain. There's a region of the brain called the fusiform gyrus. And in that fusiform gyrus, there's a face area that has been named the fusiform face area. So these are right on the money kind of names. So the fusiform face area, and it's called that because it's an area in the human temporal lobe that seems to has evidence supporting the idea that it is specialized to respond to faces. So much like chess experts have areas of the brain that are specialized to respond to chess positions, this fusiform face area seems to have neurons that are specialized to respond to faces. So the question that psychologists and cognitive psychologists wanted to answer was, is this area just for faces? Or alternatively, is this area just for highly, highly trained stimuli? because one of the challenges for this area is that faces are both. So faces are faces. So number one, check. But faces are also highly trained stimuli. Because again, think about how important faces are to your daily understanding. Is this person angry? Do I know this person? All of that determines how you interact with somebody. Think about the number of faces that you see on a daily basis, including the people that you interact with, including your own. And think about how often you see faces. I would imagine that most of us have not gone a single day of our lives without seeing another human face. And I don't know how many other things we can say that about, right? So whether you looked at yourself in the mirror or you looked at somebody else, in the world, we've probably not gone a day without seeing a face. So it could be that we've just been playing the face game, for our entire life, and we're experts at it, and that's why we have that dedicated brain area. So let's take a look at some of the research that actually supports one side or the other side. So we'll start off with the original study. So the fusiform face area, a module of human extrastriate cortex specialized for face perception by Canwisher et al. And they were the ones that did the original research on this. And they basically had a bunch of different conditions where they compared faces to others. So you can see in that top left there, let's zoom in on it. We have faces versus objects. And in these brain scans, what you would do is you would show faces and then you would show objects and you would measure the brain activity for both of those conditions. And then you would subtract away all the brain activity that was occurring when you were looking at objects. And whatever was left would be what was occurring just for faces, right? So that little region right there, when you take the brain activity for looking at faces and you subtract out all the brain activity that you get when you're looking at objects, you get that little activation right there. And remember, 35 milliseconds is a big deal when we're talking about attention. That much activation in your brain is a big deal when we're talking about cognitive psychology. So that was for faces versus objects. And they continued to try to figure out, well, is this thing specifically for faces? So they did a bunch of different conditions. So they had faces versus objects, and it was that little fusiform gyrus area that got activated specifically. They had other faces versus objects. They had scrambled faces versus intact faces, and you still only activated that area for intact faces. So they had 3/4 faces versus hands, still that area for 3/4 faces, faces versus houses. It was just that area. That area kept lighting up more for faces compared to other complicated stimuli, in non-intact faces, other biological human stimuli like hands. It really seemed to be that was an area just for faces. However, there's always more research to be done. There's always little nuances that could be thrown in there. And another study by Gautier et al. Showed that expertise for cars and birds actually also recruits the brain area involved in facial recognition. So they took a look at bird experts and they took a look at car experts and they measured their brain activity. So let's zoom in on that. So we got 6 images of a brain here. The top 3, that's the brain of a car expert. So somebody that could look at a car and tell you, oh, that's a 1967, Ford Mustang G7 ragtop, whatever, can tell you the exact model of a car. Bird experts on the bottom 3 can tell you the exact species of a bird by looking at it, right? So we have experts at identifying these stimuli. And what they found was that, let's take a look at the top row there. Car experts in the top left, they're looking at faces. And sure enough, that fusiform face area just lights up more than any other area. However, car experts, when they're looking at cars, on the middle of that top row, bird experts, when they're looking at faces, the bottom left, fusiform face area lights up as well. All right, now let's get to the punchline. Car experts in the top center, when they're looking at cars, that area lights up. So when they're looking at highly trained stimuli, that area lights up as well. Bird experts, when they're looking at cars, no lighting up of that area. So it can't just be cars, right? Otherwise, the bird experts would have lit up there. And then car experts, when they're looking at birds, top right, no area, no light up in that area. Bird experts, when they're looking at birds, all of a sudden that area gets lit up. So in this case, it looks like, well, when you're specially trained on a particular stimulus, then you light up that fusiform face area. And Gautier et al., when they did this study, Gautier actually followed up this study with one that we're going to spend a little bit more time on as we close today. And that was the activation of the fusiform face area with expertise in recognizing novel objects. So some of the criticisms leveled against the car experts and the bird experts we'll get to in just a little bit. But some of it was the fact that these are objects that they've previously been experienced with. We don't know why the expertise was developed. So they wanted a more controlled environment. So they said, all right, let's find novice individuals and we are going to train them on identifying this novel stimuli. And the stimuli that they chose or that they created were greebles. So what is a greeble? Well, a greeble is a greeble is a entity, a thing that can belong to one of two genders. It can either be a plock or it can be a glip, and it can belong to one of five families. It can either be a samar, an osmit, a gali, a radak, or a tassio. And you would see examples of greebles, and they look like this. So that is an example of a plock from the family of samar. And here's another plock, but this plock belongs to the family of osmit. And here's a gali plock, and a radak plock, and a tassio plock. And then we have the other gender, glip. So here's a glip from the family of samar, and so on and so forth. And they had all these greebles that they created. And then what they did was, and I would have loved to be in this experiment, they would show their subjects this, and they would say, what's the gender and family? And the subject would say, oh, that's a gali plock. And they'd be like, no, that's a samar glib. I forgot the genders. But anyways, oh no, wait, I have it written down. That's a glip radak. Okay, so they would take a look at that and they would incorrectly identify it and they would get corrected. And then they would take a look at another one and they would say, oh, that's a plock tassio. And they'd be like, no. Oh no, they would say, yeah, that is a plock tassio. You got that one correct. And they would go on and on and on. And eventually, believe it or not, they would be able to identify greebles at a very, very high level. So you would be like, that's a glip gali, that's a plock tassio, that's a plock osmit. And you would get to the point where you were a greeble expert. The question is, what happened to their fusiform face area on these novel stimuli? All right, so before training in this study, there was very little response to the greebles in this fusiform face area. So when you take a look at the brain activation of these novices before training, on the left there, we have faces and we have their brain activation when they're seeing faces, and we see that very characteristic activation of that fusiform face area. And then on the right, we have the brain when it's looking at greebles, and notice that fusiform face area not lit up at all, not activated. And in graph form, we can see in terms of the fusiform face response for the faces, a very, very high response before training, right? Walking into the lab first day, that's your response on faces. Walking into the lab first day, that's your response for greebles. So very low response for greebles, very high response for faces. However, after training, there was an incredibly large response to the greebles. And importantly, it was comparable to faces. So when you take a look at the novices before training, right, notice activation for the faces, no activation for the greebles. But when we take a look at them after training, when they became experts at identifying greebles, notice that all of a sudden that fusiform face area started to light up. So it started to light up. It started to basically get recruited in the identification of these greebles. And if we take a look again at the graph of the responses before training, much larger response for faces, much lower response for greebles. Take a look at it after training. You can see that the two of them are very comparable now. Very, very close, similar activation for both faces and for greebles. So it seems that training on these greebles actually activated the fusiform face area. So the conclusions from these that Gautier et al. Proposed was that your fusiform face area, it responds to faces. That is shown. It's, nobody's arguing whether it responds to faces or not. However, they also argue that it does respond to other complex stimuli as well. So it can respond to greebles for greeble experts. It can be used for car experts, and it can be used for birds for bird experts. So any questions on the findings? All right, so we got a few minutes left. What I'm gonna do, and this seems to be a running theme, but I kind of like it. We're gonna set up some challenges for this so we can think about it a little bit, come back next time, and we'll discuss what this actually means. But I will just bring up one challenge here, just to kind of seed it in your mind. And that is the fact that with these results, when you take a look at these greebles, some of these greebles actually look like they are faces. So here's an example of a greeble, and you can put it side by side. And if you put googly eyes on this greeble, it kind of makes it seem a little bit more like it has a face. So we have what appears to be a beak or a beak-like nose. At the top of the greeble, we have what appears to be hair. So if that's the case, what does that challenge in terms of Gautier's conclusions that the fusiform face area is is also for highly trained stimuli, if some of these greebles actually could begin to look like faces? So I'm going to leave you with that. But before I leave you with that, I do oftentimes have these ideas. Some of them are on my own. Some of them, if I can locate the result, I will cite it. And the idea for this actually came from here. So I will leave you with this as we end today.
These are my ferns. I put googly eyes on them also. Most people don't put googly eyes on their ferns. I do.
All right, I put googly eyes on my greebles. But yes, so that is your challenge. If the greebles, some of them look like faces, does that change the interpretation of this result? And can that be applied to the car experts? Can that be applied to the bird experts? Think about that, and we will pick it up from here when we meet next time. But other than that, we are done for the day.